is graphs, obviously. Another is big table type. Cassandra fits into that. And then there are key value stores. So React would fit into that. Amazon's Dynamo would fit into that. And document stores, obviously Mongo is probably the most well-known NoSQL database that's out there. Graphs focus on a specific type of area, and that's the relationships within data. And before we get into the agenda, just a little bit of background on me. I've been developing for about 15 years, working with graph for almost 6 years now, working on my PhD, and I wrote a book called Practical Neo4j, and that's where my advertising ends. We'll jump into the agenda. So we'll give some background on graphs. I think that'll be good, especially since it seems nobody in the room has worked with graphs before. Talk about modeling a little bit, querying language, and then we'll dive into the app, actually get into some code. So you might recognize some of these logos up here, and the thing that they all have in common is a core part of their data systems relies upon graphs. When you use Twitter, when you use LinkedIn, when you use Facebook, you're talking about a graph. Essentially, it's representations of data that have some sort of relationship. It's how Twitter can manage hundreds of millions of relationships for your followers and who you're following. And graphs got their start about 400 years ago from this guy right here. Anybody know who this is? Okay, so this is Leonard Euler. He is the father of graph algebra, and he came up with a very important theorem on graphs, and it started with this right here. This is 7 bridges of Königsberg, and essentially the problem is you want to be able to traverse each bridge, with the red circles there outlining the bridge, without crossing any one of them more than once. He proved you could not do this. But in World War II, I believe it was the Russians came in and bombed a couple of those bridges. Now you can prove it, so that's convenient. But what he learned out of that is essentially those objects form a sort of pattern, right? And they form a graph. And when you get into relationships, when you're looking at data and you look at it in a big way, it starts to look a little something like this, right? So this is essentially a cluster representation of how Ashton Kutcher's Twitter followers might look like, right? In terms of their relationships to one another, with Ashton being in the center there. Another way to think about it from the relational database side, when you're looking at data in a relational database, whether it's in a table or whether it's in an index, you're going to have to scan the whole thing. So this is Liberty Memorial Stadium in Memphis. And if you're trying to find somebody on the 50-yard line in terms of looking at it from the relational side, you have to scan the whole thing, right? You have to look at the whole stadium. In the graph world, you're just looking at one specific set of data. You're starting with a point and having an endpoint. So if you wanted to find people that were within 15 feet of each other in a graph, that would be very easy to do. And the relationship looks a little bit like this. So you're starting from this central point and working your way out in the graph. And it's becoming so important to companies that they're making it part of their core business. And that's why Facebook has invested so much time and effort into building out their own proprietary graph. And that's why you're starting to see the popularity of graphs grow tremendously. And this is from just last month. There's an index called dbengines.com that looks at the popularity and interests of different types of databases. And some of the common use cases for graphs are transportation and logistics. As you can imagine, a graph with relationships like that, it looks like a map, right? Roads and destinations and starting points. In healthcare, we look at patterns of care. We want to understand which patterns of care deliver the best outcomes, otherwise known as efficacy. In finance, we want to look at patterns of transactions. It's one way to look at fraud, for example, in real time. And consumer and retail is probably the best known, right? All of the social networks, all of the dating websites. 8 out of 10 of the biggest dating websites use graphs to do matching. And Amazon uses it. They have their own proprietary graph. 1/3 of their revenue is generated from using graph databases. When you go onto Amazon and they say, hey, you should buy this product because it goes really well with the one you're about to buy. Or people who bought this product also bought this other product. It starts to be able to tie all those things together. And eBay's used it for their on-demand delivery service. When they started the service, they essentially wanted to create 15-minute slots. So as a mom and pop operation, you can go in and pick one of those delivery times to have your stuff moved across Little Rock or moved across Memphis. When they started out, to create that page of delivery options, it took 2 minutes, and they could only put out 2,000 delivery windows. When they moved over to a graph, it took 2 seconds, and it created 40,000 delivery options for them. And this is their lead developer on the project. He said the graph was literally 1,000 times faster, and he used the word literally correctly, 1,000 times faster than their relational database. So it has a lot of use cases, but there are places where it does not make sense. I'll let that soak in for just a little bit. Yeah, this is a representation of something that does not make sense. If you already have well-formed data, if you have less than 2 million records, if you're not doing a whole lot of joins, it doesn't make sense. So we'll look a little bit at graph modeling. Jump over here. Stand by. Technical difficulties. So we're going to look at a couple of models here to get you acquainted with it. Who uses relational databases as part of their job? Okay, good. So we're going to do some contrast and compare on models, and then we'll do some contrast and compare on SQL and the querying language for Neo4j, which is called Cypher. So what you have here is essentially a Twitter or Facebook type model where you have a user over here and their friends over there. So you'd have those characteristics or columns that you'd have in the relational database side, and then another table to represent essentially kind of like a join type table, right? In the graph world, it works a little bit like this. So every type of object that is in the graph that's not a relationship is called a node, and every node can have a label. It can also have multiple labels. So in this case, we have 2 people that have a relationship of friends, and it is a directional relationship. You can have bidirectional relationships as well. So in Facebook, if you're friends, it's a mutual type of connection. On Twitter, it's just a one-way type of relationship. So here's the one-way connection that you might have like in Twitter. And here's something called an interest graph. So you have a user here that has interest, and they're joined together in a table. And it's simply represented like this in a graph. So you have a person, you have an interest, and user interest is the relationship. So it's a typed relationship that connects them. And you can also store properties on the relationship. So one way to think about it is relationships replace joins. They're a little bit more complicated model. This is a consumption graph. So this is something Amazon or a retailer might use on their website to understand what you're looking at, right? Or if you run a content website like Medium uses a graph to understand what's interesting for you and make recommendations. So you want to have a user, you want to have products or content, and then you want to connect them in a join representation in a table. It was simply done like this in the graph. So they viewed something, whether it can be content or product. So that's a really powerful representation, right? Look at the complexity of this model in a relational side. And that's how it is in a graph. It's very simple. And you're reusing relationships, right? They can view anything, a product, content, videos. You can start to get very fine-grained in tracking that. So it's a very, very powerful tool, especially when you start to look at very complex relationships. So here's an intent graph, right? One of the things that we do at Graph Story is look at predictive modeling, right? You have essentially 3 types of analytics out there. Descriptive analytics, which are table stakes, right? Stuff you already know. Here's what we sold today, right? Then there's predictive analytics. What do we think we're going to sell? What do we need to put in the warehouse? And then there's prescriptive analytics, where you're taking it a step further and feeding information back into the predictive model. So this is getting more on the predictive model side. This is how you'd represent a predictive model in a relational database. pretty complex stuff. You have products, you have orders, you have order items, you have users that have addresses, they have folks that they might follow or have some sort of relationship with, they have interests, things they've searched on. You represent in a graph, it's pretty straightforward. You have nodes that are connected by very discrete relationships. A user has interests, they have friends, they live at a location, they've made purchases that contain products. So I'm going to jump a little bit into the language side. And Cypher is essentially, it's a declarative language. It's very similar to SQL. It doesn't necessarily enforce how, but more of the what that happens. So here's a basic Cypher example. It looks a little bit like ASCII art, where you have an object on one side, in this case content, that has a tag, right? So if a hashtag or something like that. And you represent each of the objects with a variable and a colon to denotate that variable. And then each has a label that would be tied to it, and there's a relationship and a direction. And you can also have properties with parameters that so you can do lookup. And you can create indexes on all of these nodes so you can do really, really fast lookup. Under the hood, essentially it's Lucene, same thing that's used in Elasticsearch. And then you return variables, whether it's the content that you want to return or the tag or all of the relationships. Simple example how to create an index. What you do is have the node label and what you want to index on. You can also drop indexes from Neo4j. And you can create constraints as well. So if you wanted to make sure that something was unique for any node, essentially you create a constraint and you assert whatever you want to be unique. And you can also drop those constraints. So a little bit of a one-to-one comparison with SQL. You can see here, select full name, email, username from user where username equals Greg. Everybody's pretty familiar with this, I'm guessing? No? No? Yes? Okay. And the same thing in Cypher. So one thing that you can do here is if you wanted to return just everything about that user, you just return you, but you can get fine-grained and say, I just want these properties back. And essentially doing a match on username marker. Here's the where attribute. Very similar to SQL, you would put it after a match. You want to see where active equals true. You could also do wildcard type of searches, very similar to SQL. And just like in SQL, you can do things like order by and skip and limit, so if you want to do paging. But one of the really, really cool things about Cypher is it has this command or expression called with. So if you wanted to get a certain portion of the graph and then start to kind of split it out, you can use with to do that. So essentially you're passing part of the graph into the next piece of the query. You can think of it kind of like a subquery where you do a where statement inside of a where statement. There's a create option. Here's an insert into user for Greg. Same thing on Cypher. Instead of insert, you use create. To do an update in SQL and to do an update in Cypher, pretty similar. You're going to use a set on whatever property you want to add, and then you could pass that back once it's been updated. And delete works pretty similar as well, where you're going to do a match on whatever you're deleting. You can also get a little bit more fine-grained where you want to be able to delete the relationships. And one thing to note here is if a node does have relationships and you try to delete it, like in this example here, it won't work because it wants to maintain the integrity. You have to delete the relationships as well. Okay, that wraps up the presentation for today. I appreciate everybody's time. I'm going to stick around for a few minutes. If you have questions, or if there's one you want to ask right now, feel free to. Otherwise, you can come on up and we'll hash it out. Thank you very much.